And welcome back, and we are preparing for the main event, as it were. This theorem really is what we have been building up to. It was proved in a paper by Christensen, Simon, and Zinchenko, and I'm going to even improve on it just a little bit. So, we were told we've got a set E and R, and supposing it's a regular Perot-Widom set. Now, first off, what the heck is Perot-Widom? Well, PWE is just the sum of the Green's function for E at every point where that is a critical point of the Green's function. So, assuming that the Green's function has a finite number of critical points, or at least that its sum is finite, that's what's called being Perot-Widom, that sum is finite. Frankly, I have trouble imagining a case that wouldn't be. I'm sure they exist, but we're going to try to prove this and even prove something a little better, because we're going to relax the regularity condition a bit too. So the idea here is that we like to know what the maximal error, the Chebyshev norm, is of a set E, and this way we could figure it out without having to actually construct the Chebyshev polynomials. So if the capacity is 1, we would have an upper bound for all the Chebyshev norms for n. If the capacity is less than 1, then this thing would converge to 0 rather quickly. If the capacity is more than 1, it's probably not all that useful, but we can often rescale to make the capacity be 1. So let's get started on working through this idea. Well, first I just want to have a little refresher about the topology of E. So we started off, E is compact, and we'll say nonpolar. We probably could use some of this with polar sets, but for example, the last thing talked about the capacity. If the capacity is 0, I don't know if that would hold up so well. So we'll just assume it's nonpolar, which also implies uncountable. And the thing to think about is that where E is an R, so if we broaden our scope, our perspective to C, then E is all boundary. When we talk about the boundary of a set, that is to say, the part of a set where if you pick any point, if you draw an open circle, you will automatically get points that are in the set and points that are out of the set. Well, we're in the complex plane, an open set is a ball, so no matter how we draw it, it's going to spill over into the non-real part. So because it's all boundary, that means the Green's function of x is 0 for quasi every x that's in E. All the boundary. And that means all the set, except for a small exceptional set, a polar set. So we'll split it up into E being E naught union set of xi, where I can go from 1 to m, and m is some number between 0 and infinity. So I think I talked about this last time, that we're going to allow there to be possibly infinitely many points where, let's see, E naught is regular. So E naught is the regular portion, the portion where the Green's function is 0. So all the exceptional points are peeled off here, and we're assuming there's only countably infinite many of them, or fewer. So what do we know about this? What can we say about the Green's function? Well, we can say that the xi must be isolated from E naught. What do I mean by that? Well, I mean, if there's a point here, xi, and when you plug into the Green's function, you get a positive number here, ge of xi is some epsilon greater than 0, and there's got to be some delta here, where ge of x is greater than epsilon halves on xi minus delta xi plus delta. And since, by definition, ge is 0 on E naught, we know that E naught must be out here somewhere. So these points where g is not 0 must be isolated from the points where they are 0. It can't be right up against it. It can't be a limit point. Now, E naught and E could be complicated. When we're I generally think of them as intervals, but there's no real requirement for that. We will know that E will have gaps, unless it was just a single interval, and that's simple enough that we don't really need to do much of this for it. We'll have gaps, that is, connected components of R without E. I guess bounded connected components, because we're not counting the part outside of the whole of E that goes off to infinity. It's supposed to be a slash from minus sign there. So, what kind of stuff will happen on these gaps? The gaps are actually going to be key to our proof here. So, let's say here is some point in E naught, and here is some other point in E naught, and in between there's a gap. What will the Green's function do on this? Well, there's really only one choice. It's got to go up and come back down. And so there'll be a max in the middle. Now, what if, though, the gap isn't in E naught? What if here's another point in E, but it's an irregular point? Well, then the Green's function might go up to here. So in this case, the max is at the end point. So we've really got two choices. On each gap, Green's function is max at a critical point or an endpoint. And we will look at this a little more in the near future, because it will actually be the key to everything we're doing. We're trying to minimize some error, and we'll do it by finding a bound on the Green's function. Now, I do want to remind you, though, we've also got something called En. En is what I refer to as E and its cousins. And it is much simpler. It is at most 2n intervals. We talked a lot about this way back in the first video of this lecture series, so I'm not going to go too heavy into it here. I'm going to remind you with the examples, one of the examples we had. We had our Chebyshev polynomial. Remember, that's how this all started. It's talking about Chebyshev polynomial, which had some sort of alternating set like this. This is where we were assuming it was negative 1 to 1 union 2. And so we said maybe a polynomial looks like that. It goes down, back up. Then outside, maybe it goes way up and then back down before finally hitting right here at the third alternating point. We said if that were the case, then this band here, we want to include other points in x that also get sent in that same band. So we would extend it to this. Thus, what started as an interval and a point became two intervals. And that's because if we include this point, where it was on the band, it was supposed to be on it there, then we have to include points near it, some of which will be in the band. So En becomes at most two intervals. In this case, we gave two intervals, but it could have been as many as 6. We said En was Tn inverse of Tn of E. So we take E, we apply the Chebyshev polynomial, it will give us a band of some sort, and then we pull back to all the other points that get sent into that same band. So the reason we like En is because its topology is much simpler. It's just a set of intervals. We don't have to worry about all sorts of weird isolated points and such. All right, so to prove this, there are two things we are just going to take as given, and maybe someday I will circle around and prove why they are, but right now I'm just going to state them. This is called 1.7 in the paper I have. And it says this: if f is continuous on E, there exists a unique function u sub f that is harmonic on C bar without E, so that's everything except E, including infinity, which approaches f of x for quasi every x in E. So that's the Dirichlet problem. It's a solution to that. This is very similar to the Green's function. I'm sure you're recognizing. At least I hope so. And we have a closed form for it. UF infinity equals the integral along E of f of x d rho E of x. So like I said, I'm not going to prove this. You can take a screenshot if you like. But it feels similar enough to what we've done with Green's function that it seems pretty plausible to me. We have a harmonic function that's harmonic outside E, and if we take it to infinity, we get the integral over E with respect to the equilibrium measure. That's what this is, the equilibrium measure here. So this does feel pretty familiar. We saw that we could sort of with a potential, this was a log of absolute value of z, which turned into a green function. Or I'm not sure I can really state this eloquently, but I hope this at least tickles some memories of you about how we constructed the greens function for these sets. The other piece of information that we're just going to take as given is an inequality which states that the absolute value of Tn E is less than or equal to 2 times the capacity of E sub n to the n power. So if we had E sub n, we could work out the capacity of it and raise it to the nth power. That said, it would be nice if we could replace that with just capacity of E, because then we'd have to do one calculation instead of having to redo it every time. So we're going to try to, first off, use this property, this 1.7, but you can write this down if you need to, this second one as well. But we're going to use this 1.7 and try and apply it with the greens function. All right, so let me erase everything here. So, first off, we have said that G E of Z is the same as G E naught of Z. E and E naught are differed only on a polar set, and since the definition of Green's function, or the characterization of Green's function, involves what happens at all limits at all but a capacity zero set, since they're only different on capacity zero set, they are going to actually turn out to be the same function. So what this means is that GE of Z is 0 on E naught and harmonic outside E naught. Therefore, it's continuous on E sub n. Think about that for a second. We've got E naught, it's 0. That's part of En there. And then the rest of it is outside of E naught, so it'll be harmonic and therefore continuous. So the GE of Z is going to be the F in that previous example, or yes. And we're going to try to find the function that is harmonic outside of E. Excuse me. So here's how we're going to do this. I'm going to say let's define H of Z equals GE of Z minus GEN of Z. Now I remind you that E is necessarily a subset of En, so H of Z will have to be 0 on quasi every point in E. Because if it's in E, it's also in En, so both those functions are going to be 0 quasi everywhere. But actually we can improve this. En is regular. And the reason for that is that it's just intervals. You can't really, we said irregular points have to be isolated from their set. If we had a bunch of sets here, a bunch of intervals, you cannot have the Green's function be non-zero on one of them, because it would have to be a non-zero on a whole interval, and an interval has positive capacity. So there's no way that En can have any irregular points. It can't have G be non-zero anywhere. There are no isolated points. So that's great, because then we can knock out that quasi-every part there. All right. So for x in En, the limit with zeta going to x of GE of zeta will equal limit zeta to x of GE zeta. I'm sorry, I messed this up. This is supposed to be h here. Minus GEN of zeta. And so the En part will have to go to 0. So this ends up being GE of x. G is continuous on En, so that the limit goes in that way. If x is in En, then that Green's function zeroes out. X being in E, En does not necessarily make it in E, so this part might not be 0. So therefore, we get GEX there. Now, the Green's functions are all harmonic. So, okay, so this gives one of the properties that we had for that 1.7, that property of it approaching 0, or approaching the Green's function, excuse me. So H approaches GE on E. En, I believe. Yes, H approaches G on En. So that was the first part of that 1.7. Is H harmonic? Well, GE and GEN both harmonic. Outside En. What about at infinity? We need to check at infinity. That was part of the rule. Well, let's see if we can work that out. All right. Now, H of Z, if we remember what the Green's functions do as they go out to infinity, they approach log of absolute Z plus a constant. And it turns out we can even specify a little more. It is, the constant is R of E. That is the Robin constant. We also called it VE in some of the other videos. Plus an error term on the order of that, 1 over Z. So this is just a little more specific, a little more detailed version of stuff we've done before. Plus R E sub n plus another order of 1 over absolute value of Z. So what happens if we take this to infinity? Limit as Z goes to infinity. Well, those are going to cancel for sure. And these will both go to 0. So we are left with R of E minus R E sub n. So that limit exists. It can be removed, which means the removable singularities theorem, it says that H is harmonic on, what was it? We said C bar without E. So they just both the Green's functions just naturally inherit the fact that they're harmonic. So their difference is harmonic as well. And then since we go to infinity, since a Green's function always turns into this log form as you go near infinity, so the difference cancels out those logs and we're left with this constant here. So the H we have is the solution to that Dirichlet problem. And that means we can plug it into that 1.7. But before I do that, I want to rewrite this because the specific value will be useful. It will remember RE is the same as the log of one over the capacity minus log 1 over that capacity. That was just how it was defined, or capacity was defined as e to the negative r e. So, and then just use, basic log rules. This becomes log of capacity of E sub n over capacity of E. So that's what the H infinity is. And we're going to use that in a minute because our whole thing was that the function evaluated at infinity gives a closed form of the integral. So that was, if you'll just go back to that 1.7, if you have the screenshot, it was H of infinity equals the integral E sub n of the Green's function of E, not of E sub n, the Green's function of E, d rho n of z. We're juggling between these different Green's functions a lot. And the way the general theorem, that 1.7 was written, it may be different than it looks. We're plugging in different things into the formula, so they may not match the way you were expecting. So read it closely. Now, we know what H infinity is, but we're going to try to come up with another form for this. Now, we know that GE of Z is going to be equal to 0 on most of E. So let's denote the gaps of E as Kj. J equals 1 to m. And again, there could be infinitely many of these gaps. Now, the Green's function is non-zero on these gaps. All right, so let's work out what that integral was. The integral across En of GEZ. So that'll be the sum across the gaps of integral across each Kj of GEZ d rho n. So what did I just say here? Well, what I said was that we're integrating across En. If we are inside E, then the Green's function is just 0. So we don't even need to bother with those integrals. We don't need to bother integrating across the parts of E. So we're just going to integrate across the gaps of E, with understanding that these gaps are all subsets of En. All right. Now, what is this integral going to be? If we're going to integrate across Kj, the function Gez d rho n of z, well, it's got to be less than or equal to the max on that set, the max across all the x's in Kj, of the Green's function of x times rho n Kj. So here's all I'm saying. Integrating a function across a set Kj with respect to some measure, it's got to be less or equal to the highest possible value on those Kj's, on that Kj, evaluated there, times the measure of that Kj. In the Lebesgue terms, it'd be the width of the interval, or whatever measure we have here, which is probably not width. And then we have one other fact that we're just going to state, which is that we know something about the measure of the intervals. That specifically, the gap here is less than or equal to that same max x in Kj of Gex times 1 over n. This is just given the harmonic measure. We split it up into gaps for n here. Then it's going to be the equilibrium measure of each gap is going to be less than or equal to 1 over n. So then we plug back into that. H of infinity is less than or equal to, well, let's pull that 1 over n out, 1 over n times the sum from j equals 1 to m of the max across x in the Kj of the Green's function. So then just plug that in. We know what h infinity is. So log of c of e sub n over c of e is less than or equal to that same 1 over n sum j equals 1 to m of the max of x in Kj times the Green's function of x. So we've managed to use a fact about Green's functions, harmonicity, and the like to connect the limit here of the difference of two Green's functions with the maximum value of the Green's function at every point in the gaps. And then we can just do some basic algebra to juggle this around. Let's multiply by n on both sides. Then let's carry it up. And we'll go up here as a power. And then we can cancel log using exponential. So c of e sub n over c of e, all raised to the n, is less or equal to the exponential of the sum of the max across each kj of the Green's function. We can move that over to our side, so ce sub n to the n is less or equal to that whole exponential of the sum of that same max. This is tedious to keep writing, but I want to be clear. X times c of e to the n. And then let's multiply both sides by 2. Put a 2 here and a 2 here. Then earlier we said we already know that this thing is greater than or equal to Tn. So that gives us what we want, really. Tn sub e is less or equal to 2 times the exponential of the sum max across x n k j from j equals 1 to m of the Green's function of e at x times c of e to the n. So that's our bound. We've got a connection between the Chebyshev norm and the Green's function. All that's really left is to evaluate this sum, or give some other form for it. And we kind of alluded to this already at the beginning, that the Green's function, we've only really got two options. Either, for some, let's say, kj here, either it contains a critical point. Let's say there's a critical point here, c sub j. Then the max on kj is the Green's function at c of j. If there is some critical point, some place where g prime is 0. So if kj contains a critical point for Green's function, then that critical point is the max. If kj does not contain a critical point of the Green's function, the Green's function has got to be monotonic. It can only have one max in each gap. So if on the gap there is no critical point, then it must simply be monotonic across there. So the critical point is at one of the endpoints. Now, GE is now non-zero on here. So this max point, kj is a gap of E, which means these endpoints are both part of E, so this must be an irregular point. So that is saying that if it's not a critical point, if the max is not a critical point, then it's an irregular point. So think about what we're saying here. We got two endpoints. Maybe they're regular, maybe they're not, but if there's a critical point somewhere, it must be the max of the Green's function. If there's not a critical point somewhere, then basic calculus says the max must be one of the endpoints, and that endpoint is in E, which makes it an irregular point of E. So that means that every maximal point is either an irregular point or a critical point. So I'm going to say, then that is saying, that shows us that if we sum, sorry, let me draw this properly. If we sum from j equals 1 to m, the maxes x in kj of GE of x, that's going to be less than or equal to PWE plus IR of E. And I'm just introducing some new notation here. I'm going to say IR of E is the sum of the Green's function, all the different xj's that are irregular points. So what I'm saying here, if I go across every single gap and I add up the Green's function, all the maximal points, that has got to be, each of them is either in this set of critical points or this set of irregular points. So therefore the sum is less than or equal to the sum of the two. Now on the other hand, well, okay, and if it's if x could be both a critical point and an endpoint, I should say. What if the Green's function did like this? And say this is some xj. Well, then it gets counted in both of these sets. But I think that's okay, because this point will then be the max of two different gaps. So it's okay that it's counted twice. Now, conversely, let's say xj is a critical point or an irregular point. All right, so if it's critical, then it's a max. We said that already. If it's irregular, then that means the Green's function is positive on some xj, that's worse, on some interval around xj. Now, if it's not a critical point, the Green's function must be monotonic, which means it is an endpoint. Okay, this was the max. It's either there, or maybe it's more like this. But if it's not a critical point, if it's an irregular point, then it's got to be an endpoint of some gap. And I think what that shows then is that the max, the sum of the maxes, of GEX is greater than or equal to PWE plus irregular points of E. So this is saying, in this case, each point that's either a critical point or a regular point will become a max. So adding them up, we'll get all the maxes, which makes the less than or equal. So we had equal in both directions, or greater than equal and less than equal. So that means we can substitute in that sum that we had earlier, sub it in directly. Tn of E is less than or equal to 2 exponential of PWE plus IR of E CEN. Or if you prefer to write it this way, assuming the capacity is positive, that the Chebyshev norm, let's be really careful about this. The Chebyshev norm, which I got wrong several times, is if you were to take this to the 1 over n power, I'm mixing up my vocabulary. For some given n, Tn has a Chebyshev norm on E. The limit was the constant for the whole set, the Chebyshev constant for E itself. And that involves a 1 over n power. We're not using the 1 over n power here. But this property, this ratio of the nth Chebyshev norm divided by the capacity to the n power is bounded above by 2 exponential of Pw of E plus IR of E. So, this then gives us, this thing on the left is finite if both PWE and IRE finite. If they're both infinite, or either one of them is infinite really, then this doesn't tell us very much. So this gives us an upper bound. If these things are finite, then this ratio is necessarily finite. So if there are only finitely many irregular points, then we'd only need to look at this piece. Now, the remaining question is, what about a converse? What if this thing is finite to begin with, does it tell us anything about this? I am still working on that, and I will get back to you if I figure it out. All right. Thanks for listening.